Hey, it's Arshabir, and today we are diving into thermal deformation simulation with Abaqus CAE. Whether you are an engineering novice or an expert, we've got you covered step by step. So join us for a fascinating journey into structural behavior and simulations. A beam exposed to temperature differences can indeed experience deformation, and this phenomenon is known as thermal expansion or contraction, depending on whether temperature is increasing or decreasing. For example, when a material is heated, its particles gain energy and vibrate more. This increased vibration causes the material to expand, and the amount of expansion depends on the material's coefficient of thermal expansion, which is a material-specific property. Conversely, when a material is cooled, its particles lose energy and vibrate less. So this causes the material to contract or shrink. Here you can see an example, and as you can see, when a beam is exposed to temperature differences, one side of the beam may be at a higher temperature than the other. This temperature gradient across the beam can lead to deformation. If the beam is free to expand or contract, it will deform accordingly. This deformation can result in bending, wrapping, or changes in length depending on how the beam is fixed or supported at its ends and along its length. So engineers and architects often need to account for thermal expansion or contraction when designing structures to ensure that the resulting deformations do not cause serious problems. Materials with lower coefficients of thermal expansion are less prone to significant deformation due to temperature changes. Additionally, expansion joints and other design features can be used to accommodate thermal deformations in a controlled manner, preventing damage to the structure. You can see our problem here, and our beam is expected to experience temperature differences in these two elements you can see here. Let's begin by creating a new part in Abaqus CAE. I have created a part here, and from here you can see I have wire as base feature, and I have a 2D planar structure which is deformable. Here I have created my sketch using these tools. Here I have created some lines, and then I have added dimensions. Here you can see the dimensions, and moreover I have added an equal and constraint in order to make these two elements to be equal. A part in Abaqus represents the geometry of the structure you want to simulate. You want to create a simple beam or any other shape. You can create your desired shape here, and the first step, we must create the fundamental building block of our simulation known as a part. This is where we define the geometry of the structure we want to analyze. Okay. The next step is property, where you must specify crucial material properties, and I have defined Young modulus and Poisson ratio mechanical features, and moreover I have added value of expansion coefficient. This coefficient tells the software how the material responds to temperature changes, a key factor in our thermal deformation simulation. The coefficient of thermal expansion is a material property that quantifies how a material's dimensions change in response to a change in temperature. In other words, the coefficient of thermal expansion indicates how much a material will expand or contract when it is subjected to a temperature change. It is typically expressed in units of length per unit temperature change and is different for each material. In the next step, I have created a section here. Can see a section, and I have defined a profile for my beams section. I have entered the values of the parameters, geometrical parameters, and here I have an I-shaped profile for my beams section. Then I have assigned section, you can see it here, and finally I have assigned beam orientation. In final element analysis, especially when you are simulating beams and truss elements, it's essential to correctly define the orientation of the beam elements within the 3D space. The assigned beam orientation tool in software like Abaqus CAE allows you to specify how the beam elements should be aligned or oriented in relation to the global coordinate system. And here you can see the beam orientation, and you can change them and flip them. This orientation is crucial for accurate stress and deformation analysis. Okay. Next step is all about assembling different parts or components if your model requires it. We must ensure that everything fits together correctly, just like in real world structure. But here I have only one part which is created from the instances here. You can use the tools here in order to assemble your parts together. Then I have created a step here, and each step represents a phase of your simulation. And for thermal deformation, I have set up a step to introduce temperature changes and observe their effects. The type of my step is static general, and the next step I must define loads and boundary conditions. Okay, I have boundary condition here, so I choose this one, and I select the node here, and I can add a rotational degree of freedom. To apply a boundary condition in Abaqus such that one end of a beam can move along a surface with a 45-degree slope, I can create a point here. You can see this node here, the first step. Then I need to apply boundary condition. So here I choose a node here, and I must create datum coordinate system. I select the origin of the coordinate system, and as you can see here, I have a coordinate system which is rotated 45-degree relating to the global coordinate system. Okay. So I have created a coordinate system that aligns with the direction of the 40-degree slope, and this coordinate system will serve as a reference for defining your boundary condition. So for this I have 2 degrees of freedom which are represented in my defined coordinate system, and it is added here. In the boundary condition step, we are about to introduce the magic ingredient of our thermal deformation simulation: temperature. We see temperature differences can make materials expand or contract, and this is precisely what we want to understand. So we need to specify how these temperature changes affect our structure. So for this I choose creating predefined field, and from the other I choose temperature as my predefined field. I select all the elements here, and I suppose that my temperature in initial condition is 0, and again I choose temperature from here, and I choose this element here and this one, and enter value of 50. Okay, we are done here, and we entered specific temperatures at key points within our model. These temperatures represent the environmental conditions we want to simulate. For example, if one end of our beam is exposed to a higher temperature than the other, we must enter these temperatures accordingly, and the software will then take these temperature values into account and calculate how the structure responds. Mentioning that in the context of finite element analysis for simulation, the section variation here In the context of defining a predefined field for temperature differences typically refers to how the temperature varies within the cross-section or thickness of a structural component. When you define a section variation, you are specifying how the temperature changes across the cross-section of a structural component. In many materials and scenarios, the temperature may not be uniform from the surface to the core. Different parts of the cross-section might experience different temperature gradients or profiles. And moreover, for distribution in the context of FEA, the direct specification choice for temperature distribution typically means that you are directly specifying the temperature values at specific locations or nodes within your model, rather than using function or gradient to determine the temperatures. Okay, we can go furthermore, and for meshing, step number 6, which involves diving our model into smaller elements to make the analysis manageable. We must create a mesh to represent the structure more effectively. So for this, I choose 0.45 as approximate global size, and suppose it's okay, and I apply the mesh to my part instance. Then I can create a job here. The last step, we must set up the analysis job and launch the simulation. This is where all our preparations pay off, as we watch the software calculate and show us the results of our thermal deformation study. So I create a job, and here I can submit my job. The monitoring option allows you to track the progress and status of your simulation job while it's running, and it provides real-time information and updates on various aspects of the simulation process. Okay, our simulation is completed, and we can watch the results here. As you can see, our beam has experienced a significant deformation. Okay, if you found this video helpful, don't forget to give it a thumbs up and share it with your friends and anyone you think might benefit from it. Your support is what keeps this channel going and it motivates me to create more educational content. Thank you for your watching.